Your smartphone is dead. The battery is drained, the screen is completely dark, and it won't respond to your touch. Yet, even in this powered-down state, thousands of your photos and apps are being held perfectly in place. To see how that's possible, we have to look past the glass and focus on just one tiny pixel of a single photo. That single dot of color breaks down into 24 separate pieces of digital information. In computing, we call these ones and zeros. Scaled up, a single photo requires millions of these microscopic 1 and 0 switches to exist. These millions of binary switches occupy a specific physical architectural space within the hardware of your device. To find that space, we travel through the layers of the phone until we reach the smooth, flat silicon surface of the memory chip. Early memory chips were like a flat suburban neighborhood, storing data on a single-story 2D grid. But you eventually run out of land. Once data reaches the physical edge, you can't add more memory without making the phone too large. To fix this, engineers developed a design called 3D NAND. This diagram shows the shift in perspective. Instead of building outward, the memory architecture builds upward, creating vertical towers that stand 136 stories tall. Stacking the storage space vertically allows a massive digital library to fit into the small footprint of a modern phone. With millions of data bits rushing into these towers, the chip needs a way to organize traffic so everything lands in the right spot. The chip uses bitlines, which act like information superhighways. These pathways route incoming data across the chip at incredible speeds. Positioned along these highways are control gates, which function like a series of automated traffic lights. You can see the process here. The control gates flash green at precisely the right microsecond, directing each bit of data into its assigned vertical layer without any collisions. This precision management prevents the data from bunching up or ending up in the wrong tower, which would cause the file to become corrupted. If we follow one of those data bits to its destination, we can see how it's actually stored inside a single room of the tower. Inside the charge trap, an electron pushes through a barrier into a central chamber. The barrier then becomes an insulator, physically walling the electron in. This dictates the data. A trapped electron represents 0, while an empty chamber represents 1. A moment of clarity. Because the electron is physically barricaded by these insulating walls, it stays exactly where it is, even when the electricity is turned off. Relying on these physical walls rather than a constant flow of electricity, the charge trap holds your data regardless of the battery's charge level. These microscopic traps are designed to hold those electrons in place for decades. When we reverse our journey, moving out of the trap, past the skyscrapers, and back to the surface of the phone, the scale becomes clear. As soon as you connect a charging cable and the phone powers up, the system reads the physical location of those trapped electrons to reconstruct your photos exactly as they were. Your digital life is preserved in this tangible, physical, 136-story metropolis inside your pocket, waiting for the lights to come back on.